Okay, Victoria is here. Victoria. Dash. Bahava. Riley. Okay, good afternoon, everyone.
Well, good afternoon, Professor.
Good afternoon.
Good afternoon.
Good afternoon.
How is everyone today?
Doing pretty good.
Okay, great.
Good.
Great. Okay. Everyone sees the slides?
Yep. Yeah.
Okay. Last time we spoke about flip-flops, and we mentioned flip-flop is the output of the flip-flop is synchronous with clock signals, which means flip-flop is a synchronous version of latch. But for flip-flop, the transition happens at the edge of the pulse. At the edge of the pulse, either positive edge or negative edge. And we mentioned when we look at the flip-flop, we can know if this positive edge or negative edge. We can see this symbol here. This symbol here for this SR flip-flop is positive edge. But if we have a bubble here at the input, this is negative edge, which means for positive edge, the changes at the output happens as the positive edge here of the clock box. For negative edge or negative edge triggered, so the changes happens as this negative edge of the clock box. We have different flip-flops. SR flip-flop, JK flip-flop, T flip-flop, D flip-flop. We mentioned SR latch or SR flip-flop is the basic of all other flip-flops. All other flip-flops is just a modification for SR flip-flop. We mentioned we have issue with SR flip-flop. What is the issue? Who remember what is the issue?
Something about the inputs can't both be 1, I think.
What do you mean by something? Be specific, man. What's your code?
3. Think.
3. Bang. Yes, bang. So what is this specific something? I mean, what is the issue?
I don't actually remember. I just remember that the inputs can't both be
Okay,
1.
so you got half point. Okay. Who remember? Who
Is the
remember?
invalid input
Invalid input for what?
For S
for the
and R,
SR?
For what?
S and R shouldn't be 1.
Exactly. Who said that?
28.
Hmm?
28.
28?
Yes.
Stephen? Okay. Thank you, Stephen. Yes. 1, 1 at the input is not allowed. S equal 1 and R equal 1 at the same time. Guys, I mentioned this many times last time. I was expecting everyone remember actually. S is 1 equal to S is 1 and R equal to 1 at the same time or simultaneously at the input is not allowed. Why not allowed? Yeah, we don't know the out. If S equal 1 and R is 1 or both of them high at the same time, we don't know the out. And we will see today in the lab. Either we can, and we did this when we follow the inputs and we look at the outputs. So in our example, we mentioned, we saw the output, Q is 0 and Q inverted is 0, which never happened. If Q is 1, so Q inverted must be 0. If Q is 0, Q inverted must be 1. But we saw something strange. Both of them are 0, which means we don't know the output and this is not valid. So JK flip-flop, T flip-flop, D flip-flop is different flip-flops to overcome this problem. We mentioned JK flip-flop. How JK flip-flop covered this issue?
It toggles.
Targets. Perfect. Thank you. What's your code, please?
7.
7. Thank you. Ken?
Yes.
Yeah, we mentioned JK flip-flop is the same as SR flip-flop, except one thing. I put here, I added this truth table just to make sure everything is clear. This is the symbol for positive edge triggered JK flip-flop. And J exactly the same as S. J acts as S. K acts as R. So J actually works as S. Let me just make sure. Okay. So J like S and S are free flow. K like R. Like R. Except the case for 1, 1. So if S is 1, I mean, if J is 1, if J is 1 and the K is 0, like S is 1 and the R is 0, set the output to 1. Set the output to 1. If S is 0 and the R is 1, reset the output to 0. I mean, J is 0 and the K is 1, like S is 0 and the R is 1, reset the output to 0. 0, 0, we mentioned no change. The new status Qn plus 1 equals the previous status, which is Qn, means no change. Here means no change, means no change. Okay. So means no change. Okay, but look at 1, 1. 1, 1, in this case, like S is 1 and R is 1, no. For JK, no. This is allowed for JK. And this is a modification happened here. For J is 1 and the K is 1 at the same time, the new output, Qn plus 1, equals the previous one inverted, which we call Qn toggle, which we call toggle. Toggled. Toggle. Okay? Toggled means inverted. It means the previous status inverted. Between the edges of the clock pulses, this means there is no zero level between the edges. So J and the K, what does this symbol means? What the symbol means? X symbol means what?
Doesn't matter.
Don't care. Perfect. So do not care. I suppose everyone knows this. We spoke a lot about don't care when we talk about Karnaugh map. We mentioned we can use this don't care as once to complete the groups. So I assume everyone knows this. I hear few people. What's your code, sir? What's your code? The one who said doesn't matter. What's your code?
Oh, 3 again. Bang.
3. Okay, thank you.
You're welcome.
So don't care means whatever J is, K is, as long as between the edges there is no change at the out. The output, which we call it Qn plus 1, is the same as the previous status, which we call it Qn. Okay, so no change. Okay. Okay. So we spoke about the JK flip-flop. Then we spoke about T flip-flop, and the T stands for toggle, which means in T flip-flop, another modification, we have always J is 1 and the K is 1. For T flip-flop, when you see J and the K always connected to high, logic high, so this is T flip-flop, means with each edge, either positive edge or negative edge, based on the type of the flip-flop, the output is stuck, like inverted. So if the previous stat is 0, the new one will be 1. If it is 1, it will be 0 with each edge. This is the function of T flip-flop. Then another modification called the D flip-flop. D flip-flop has only one input, which we call it data or delay. Why has only one input? Because between J and the K, all of them are modification for J and the K. Between J and the K, we put inverter, not gate, to avoid getting, I mean, like again, as modification for the flip-flop. So we mentioned there is major function for D flip-flop actually, because D flip-flop solves the problem and the JK flip-flop solves the problem. So the main function for the D flip-flop to get delay at the output. The processing of when we apply the input as a flip-flop, there is gates inside, there is circuit inside. So processing to get the output takes some time. Yes, this time is it's fraction of seconds, but we need this delay even in fraction of second. So this is the major function for the D flip-flop, to get the output delayed. Also, we mentioned how we get the edge triggered using this simple circuit or logic diagram. So it's called the pulse transition detector, and we will use it today for the lab. And we discussed this last time. So we mentioned here, we can see two inputs, another two inputs different than JK, pre-inverted and clear inverted. And we mentioned these are higher rank control inputs. So before we do anything, we look at these inputs first, because based on these two inputs, the only normal function, the flip-flop goes to normal function only if and only if both pre-inverted and the clear inverted are ones, or pre and the clear are zeros. This is the only case the function goes to the normal operation. Other than this, as we see here, if pre-inverted, clear inverted are zeros, this is not allowed. Okay? If pre-inverted, preset or pre-inverted, short statement. If it is 1 and clear invert is 0, like pre is 0 and clear is 1, so this clears the output. The output is 0, whatever the inputs are. Whatever J and K are, the input is 0. If preset is 0 and clear is 1, means preset is 1 and clear is 0, so set the output to 1, whatever the inputs are. And we did analysis last time for this. Then we spoke about important application for T flip-flop, which used as frequency divider. We mentioned we have clock pulse with certain frequency. Sometimes we need to get pulses with lower frequencies. So we can do that using, like here, example for two flip-flops use, so we can get the frequency, if the frequency of the clock pulse FCK, so the frequency of QB is 1/4 FCLK. And we mentioned how we get this. Then we spoke about the D flip-flop, and we mentioned we just, with each edge, we just see the data at the out. Any questions so far? This is what we spoke about last time. Okay, now we'll talk about counters. Counter is important digital component. So it is sequential circuit. Why we consider counter is sequential circuit, not combinational circuit? Why? Why, guys? Why counter is sequential circuit or flip-flop is sequential circuit?
Because counting is sequential. 1, 2, 3. I mean, you can't like skip, right?
No. This is not the reason. There is important reason differentiate.
Oh, the output depends on the input, right?
The output depends
The
on the
output
clock.
always depends on the input. But what is the difference between sequential circuit and combinational circuit?
The output depends on past inputs.
What is that?
The output depends on past inputs,
The output depends on the input.
like historic inputs, like the memory.
What is the difference between sequential circuit and the combinational circuit? What is the difference in the
It
inputs?
depends on the clock.
The clock. Perfect. Thank you. What's your code, sir?
7.
7, double points. 7. Thank you. We mentioned sequential, we have clock pulses. Combinational, we don't have clock pulses. So the output in combinational circuits depends on the inputs only. But in sequential circuit depends on the inputs and the clock pulse. We mentioned the changes happens as the clock pulses. But if you go back to multiplexer or comparator or other subtractor, there is no clock pulses. So it is sequential because we have the clock pulse is important input, and the output depends on this clock pulse. So it is a sequential circuit that follows specified pattern of output state changes, and then return to their initial state after a specified number of changes in successive clock cycles. We'll see how this happens. There are two types. There are two types of counters. Dash, you are late, Dash. There are two types of counters, asynchronous and synchronous. Asynchronous is called also a rebel counters. Asynchronous or rebel counters and synchronous. What is the difference? In asynchronous, flip-flops are not driven by a common clock, which means the clock pulse is not applied at all flip-flops simultaneously. Is not. And we'll see how. But for synchronous counters, all flip-flops are connected to the clock pulse at the same time. We'll see how. So, for example, this is 2-bit asynchronous counter. So when we say 2 bits means we use 2 flip-flops because each flip-flop for 1 bit. Each flip-flop store only 1 bit. So 2 bits means we use 2 flip-flops. So the number of counts in this case is 2 to the power 2 because we have 2 flip-flops or 2 bits. So this means this counter counts 4 counts. Start from 0, 1, 2, 3, and then repeat again. 0, 1, 2, 3, and repeat. Because it counts 4 counts, so it's called modulus or mode 4. So when we say counter mode 4, means this counter count 4 counts. And this means it is 2 flip-flops or 2 bits. So if we look at here, first of all, why asynchronous? Why asynchronous? We mentioned asynchronous means the clock pulse CLK not applied for all flip-flops at the same time. So look at here. This is the clock pulse here. It just applied for the first flip-flop. What is the clock pulse for FF1? Is this clock pulse here is CLK or something else?
It's Q bar.
Q0 inverted. Perfect. So it's not CLK. Yeah, we have clock pulse, but it's taken from another source, not CLK. So CLK is not applied for each flip-flop. It's applied on one, the first one. However, for the second flip-flop, it is clocked by Q0 inverted. Different design, different applications. But this case is called asynchronous flip-flop. I will go back to this, but let us see the difference with synchronous. You see the synchronous here? What happens? CLK is applied simultaneously at each flip-flop. Whatever, we have 2, we have 3, we have 4, is applied as clock input, CLK, as clock input for all flip-flops simultaneously. So this is called the synchronous count. But our case here is asynchronous because as we see, CLK is not applied, is applied for the first one, but the second flip-flop takes the clock from Q0 inverted, not from CLK. So this is called asynchronous. We can see the waveforms here. We have, this is the clock pulse. And so we can draw the output waveform. But before we go through this, we have to look at these flip-flops. What kind of this flip-flop? What kind of this flip-flop? To determine what kind of the flip-flop, we need to determine 2 things. Is this positive edge or negative edge triggered? This is very important because the changes happens at this edge. So if it is positive, so it happens at the positive edge. If it is negative edge triggered, so the changes happen at the negative edge. So this is the first thing we need to determine. Second, what kind of flip-flop? What kind of flip-flop we have to know the function? If we don't know what kind, so how we determine the function? So for the first one, so first of all, both of them are positive edge trigger. Perfect. Now for the first one, what kind of this flip-flop? FF0.
JK.
JK, are you sure? When J and K connected to high, what we call it? J and
A
K,
T
both of
flip-flop?
them connected to high, right? So what is it now?
T flip-flop?
T. This is T flip-flop. We mentioned T flip-flop, D flip-flop. It's based on JK flip-flop, but look at the modification at the input. Both J and the K connected to high, so this is T flip-flop, which means the output always, the output always what? Target. For T flip-flop, the output always target. With each edge, the output inverted. We mentioned this guy here. We just, do you focus with me or you are busy with something else? We mentioned this here. T flip-flop stands for toggle. In the flip-flop, both J and the K inputs are both connected to high. In this case, the new output QN plus is always QN toggle. Always. Okay, so please focus with me, okay? So, okay, this for the first one. What about the second one? What about the second one? Again, look at the connection of J and the K.
I guess it's
Isn't
also a T flip-flop.
Again, this is another T flip-flop.
Yeah.
So always the output Q1 is toggle. For FF0, Q0 is always toggle. Again, when we talk about the output, we talk about the Q, not Q inverted. We talk about the Q. So I put it here in details. So again, this T flip-flop, J and the K are always 1 connected to logic high. So the output QN plus 1 is always QN toggle. Means QN inverted. You see this inverted here? Okay. So let us see how we get the output, how we get the output waveform. So we have the clock pulse here. Immediately, we say this is positive edge. So we put arrow at the positive edge. Means the variation happens at this positive edge. Leave Q inverted, Q0 inverted, leave it now. It actually should be, it's okay, you can put it anywhere, but actually should be here between Q0 and Q1. So let us look at the output Q0 here. So initially Q0 and Q1 are zeros. Initially, the two flip-flops are zeros. Now let us look at the waveform of Q0. It goes 0 as the output until we have the first edge. Remember, we mentioned these are T flip-flops. So the new output is toggle. Means the new output will equal to the previous output inverted. So the previous output is 0. So the new one is inverted to 1. And we mentioned between the edges, there is no change. So 1 continue until we reach to the next edge of the clock pulse, CLK. So as the next edge, the new output will be toggle. So we have 1 here, we will get 0 here. Until we reach to the next edge, the new output toggle. Until we reach to the next edge, the new output toggle, means inverted. So we got Q0. Okay? Now look at the flip-flop FF1. FF1, the clock pulse for FF1 is not CLK. It is Q0 inverted. So this means we need to invert Q0. So Q0 is here, just take the invert. Means 0 will be 1, 1 will be 0, 0, 1, 1, 0, 0, 1. And now, this Q0 inverted is the CLK for the second flip-flop. So Q0 inverted represents CLK of FF1, which means the changes of Q1, the output of F1, it depends on the edges of Q0 inverted, not CLK. So now, immediately, it's still positive edge is the second one. So at Q0 inverted, we put arrows as the positive edge. We didn't put arrow here because this is not positive edge, this is negative edge. So we left this and put here. Positive edge means the transition from logic low to logic high. Raise edge. For the negative, is falling edge. So the first change happens at this edge. Initially, Q1 is 0, as we mentioned. So this 0 continue, no change until we reach to the first edge. At the first edge here, the output will be toggle, the new output. So we have 0 here, we will have 1 here. And this one continues until we reach to the next edge. Then toggle. At the edge, at the next edge, will toggle. So we got the two outputs, Q1, Q0 and Q1. Q0 here, this represents the LSB, least significant bit. Q1 represents the most significant bit. Is important to know this. So when we arrange the counts, we start with Q0 here and Q1. Q0, because Q0 is the LSB, the first bit we read. That's why I always mention when we read the bits, we read from the right side, from LSB. So at here, what is the first, at the first edge, before the first edge? What counts here? 0, 0. So 0, 0. Then between here, between the first and second, what we have? 1, 0. We start with Q0 and then Q1. So then we have 1, 0. What is the next? We have 0, 1, then 0, 1. What is next? 1, 1, 1, 1. Then at the end, we have 0, 0. So 0, 0 gives us 0, 1, 0 gives 1, decimal, 0, 1 gives 2, 1, 1 gives 3, and then repeat. Repeat again. Then 0, 1, 2, 3, 0, 1, and so on. Okay? Everyone sees the function of this counter? Any questions? Okay. 2-bit synchronous counter, as we mentioned, the main difference here, the clock is applied for simultaneously, CLK is the clock pulse applied simultaneously to the two flip-flops. So what is the difference here? There is other differences here. What you see here. What kind of FF0? Please, everyone interact with me. Please. I'm not talking to myself. I'm talking to you. So please interact with me. What kind of FF0 here?
Is it another T flip flop?
Can you speak loudly, please?
T flip flop?
T flip flop, birth. What's the code, sir?
3, 0,
30.
30.
James?
Yeah.
Thank you,
Yeah.
James.
No problem.
Series. Shut up.
Uh-huh.
Okay. So this T flip flop, okay? What is the second one?
Isn't it
Another
also
T.
a T flip flop?
Hmm?
What was the question?
Just 1 second, please. Yeah. What is the second flip flop?
Also
What
T.
is the second? Hmm?
Also T.
The second flip flop? T? Why T?
I mean it's a
Both of them,
JK
yes.
and
Both of them connected
toggle.
to Q0. But do we have Q0 is always 1? It depends on Q0. It can be 1 or 0. Right?
Oh yeah.
So if it is 1, yeah, it works as T flip flop. But if it is 0, it works like JK flip flop,
Yeah, Jake JK.
with J and the K are zeros, which means in this case, what happens at the output? If J is 0 and the K is 0, like S is 0 and R 0,
No change.
hmm?
No change.
No change. Perfect. What's the put there?
18.
Hmm?
1, 8. 18.
Please speak loudly.
Sorry, it's 1, 8. 18.
1, 8, 18. Travis? Thank you, Travis. So this looks tricky. Yeah, J and the K, J1 and the K1 connected to Q0. But Q0, it can be 1 or 0. So it is not always T flip flop or not always JK flip flop. It depends on Q0. If Q0 is 1, so JK, J1, K1 or FF1 works as T flip flop. The output will be toggle. If Q0 is 0, this means like we have J1 is 0 and the K1 is 0, like S is 0 and R is 0, so no change at the output in this case. So we have to be careful based on the connection we have. And I put more details here for this. So this 2-bit synchronous binary counter, so is mode 4 because we have 4 counts. I put here J equivalent to S, K equivalent to R, except at J equal K equal 1. We mentioned this, the output is toggle for this case. Other than this is 0, 0, no change. J1, K 0, set the output to 1. J0, K is 1, reset the output to 0. Okay. But this one here is always toggle. It's T flip-flop because J and the J0 and the K0 connected to high always. This fixed connection. We have soldering here. At this node, we have solder. This means the node, this fixed connection, always high. We have soldering here also, but the input is Q0, not one or not zero. Not one, not zero. It depends on the value of Q0, which can be 1 or 0. But I mean, not always 1, not always 0. It depends. So, node J1 and the Q1 of FF1 are connected to Q0. If Q0 is 1, so Q1, the output is Qn toggle, Q1 toggle. If Q is 0, so no change. Okay? Now, based on this, let us go ahead. So the clock pulse, both of them are positive edge, and both of them, the change is related to CLK. So we put arrows as the positive edges. Then the initial status of Q0 and Q1 are zeros. But yeah, it looks like here we have always Q0 initially is 0 and the Q1 is 0, but this is not, it can be different. It can be initial status high, logic high. If it is logic high, so instead of 0 here, we have high, 1 and 1. But we have initial status here, 0 is given. So let us look at Q0, the output Q0. So Q0, we mentioned FF0 is toggle. So with the first edge, the output is toggle. So inverted 0 inverted to 1. Keep 1 until reach to the next edge, toggle 0. Then next edge, toggle 1. Then next edge, toggle to 0. This is easy. For the second one, FF1, look at Q0 now. Q0 is the input. Q0 represents the input for FF1. So the output changes based on Q0 and, of course, the clock. So as the first edge here, initially we mentioned 0. As the first edge here, Q0 is 0. Q0 is 0. So this means the new output will change because Q0, the input, means the J1 is 0 and the K1 is 0. So the new status is like the previous status, no change. So no change, continue until we reach to the next edge. Just before, like a T0 minus, just before the edge, what is Q0? Is 1. This means J1 is 1 and the K1 is 1. So this means the output will be toggle. So the output toggle is from 0 to 1. And they keep this one until we reach to the next edge here. Just before the edge, like T0 minus. What we have for Q0? We have 0. So this means the new output at this transition, no change, because Q0 is 0. So no change until we reach to here. Just before this one here, T0 minus, what is Q0 is 1. Means toggle. FF1 is toggle, so the output is inverted. If we look at the counts, we have 0, 0. Remember, Q0 is the LSB, the first bit here, and Q1 is the next one. So 0, 0, 1, 0, 0, 1, 1, 1, 0, 0. So we have 0, 1, 2, 3, and repeat. So please let me know if you have any question. Please, if you have discussion, it's better to talk. To allow everyone to hear the discussion. But if you have a specific thing, yeah, you can chat with me. But any discussion related to the topic, it's better to talk, to allow your friends to hear you, so you can maximize the benefit of your talk. Any question here, please? Any question? Okay, now we'll talk about shift registers. Time is running. Okay, shift registers. A shift register or register is a digital circuit. It has two basic functions, two main functions can be done using shift register. Data storage and the data shift. That's called the shift register, so definitely it has a function of shifting the data. But also we mentioned flip-flop can store bits. Each flip-flop 1 bit. So data storage and data shift. One flip-flop can store 1 bit. To store n bits, so this means we need how many flip-flops? To store
N. N flip-flops.
What is that?
You need the same as the number of bits.
Yeah, the same number, of course. If we need to store n bits, we need n flip-flops. What's your code?
30.
30, James. Thank you, James. Different types of shift registers. SISO means S serial, IN input. So serial input, serial output means the input for the shift register stream of bits in series, and the output also is taken as serial in serial. Serial input, parallel output. Parallel input, serial output. Parallel input, parallel output. Okay. So this example for serial in, serial out shift register. And I put the details here to see it better. Okay. So when we look at these flip-flops, what kind of flip-flops we have here?
Looks like D flip.
D
Looks like D
flip-flop.
flip-flops.
Exactly, D flip-flop. We can see D here. This is the symbol for D flip-flop. And of course, we have clock pulses applied for all flip-flops simultaneously. So is D flip-flops synchronous and positive or negative edge? Positive edge?
Positive.
Positive, of course. Why? Because we don't have bubbles here. We don't have circles here. So it's positive. Okay. Again, the truth table for JK flip-flop is listed here. So with the clock pulse, positive edge, because this is positive edge. If D is 1, we see 1 at the out. We see the data at the out. If it is 1, we see 1. If it is 0, we see 0. But between the edges, where the clock is 0, whatever the input, no change. Qn will be the same. Qn plus 1 will be the same as before, as Qn. So let us apply here. So put arrow with the positive edges. Any question, please? Someone has question? So we have positive edges here. We put arrows at the positive edge. Then the data is given here. Then all outputs Q0, Q1, Q2, Q3, Q4 are initially zeros. So all of them zeros initially. So let us look at Q0 for the first FF0, flip-flop FF0. So we have 0, then at the positive edge, again, to determine the output, look at the what is the input just before the edge at T0 negative, as I mentioned. Like just before the edge, what we have for D is 1. So 1 appears at the output. And keep 1 until we reach to the next edge. At the next edge, just before the edge, what is the input D is 1. So 1 appears at the output. And now whatever happens for the input here, since the clock is 0 between the edges, so no change at the output until we reach to the next edge. Just before the next edge, what we have input 0. So 0 appears at the output. And continue 0 until we reach to the next edge. Just before the next edge, what is the input? Is 1. So 1 appears at the output. Continue up to the next edge. Just before the clock, what is the input D is 0. So 0 appears at the output. The same for the rest, but for Q1, the input is Q0. So this Q0 represents the input for Q1. I mean for the FF1. So Q1 depends on Q0 and the edge, not in D. So for example, Q1 0 until at the first edge here, then the input is Q0, right? So just before the edge, T0 minus, what is the input Q0? Q0 is 0. So 0 appears at the output and continue up to the next edge. Just before the next edge, what is Q0? Is 1. So 1 appears at the output. Just before the next edge, what is the input? Is 1. So 1 continue until the next edge. Just before the next edge, what is the input? Is 0. So appears 0 at the output, and so on. And so on for the rest. Taking into consideration, for FF1, the input is Q0. For FF2, the input is Q1. FF3, the input is Q3. So we look at Q3, not D. D is just for the first flip-flop. And so on. So after 5, so you can see the shift here. You can see the shift. The input is shifted. Always shifted. Always shifted, right? So after 5 o'clock pulses, as you see, 1, 2, 3, 4, 5 o'clock pulses, this is the output which we see. 0, 1, 0, 1, 1. Of course, this is the least significant bit. This is the most significant bit. So we can see this out. Okay? Any questions? Any questions, please? Okay. So we can take like just 5 minutes, please, and then we'll do the lab. Okay? So just 5 minutes break. Okay. Welcome back, everyone.
Hey,
Hello.
Hello. Everyone sees the lab?
I see it.
Okay, good. This lab about latches and the flip-flops. So we verify the functions of SR NOR latch because we use NOR gates here. And also positive edge triggered SR flip-flop. So for the first part here, this is the logic diagram for SR latch using NOR gates. And we need to fill out this table. If S is 1 and R is 0, based on what you see here. So based on our analysis, if S is 1 and R is 0, the output is 1. Set the output to 1. So you need to add another column for your measurement. So you say here like another column. And you mention like measured, okay? So you say Q is on, the output is on or off, okay? So you may add another column here to say Qn plus 1 measured. So for here is 1 based on the truth table we know. And here you should, whatever you see, you put like on or off. It should be on, of course, but whatever you see, you put for Q, and so on. When we have S and R are 1 and 1, of course, this is not allowed. Not allowed. So what you see as measured, you can say for this part here, you can see Q is off, and the Q inverted is off, for example, or both of them on. So please, you need to add one column here for the measured. Measured means what you see for the light is on or off, for both of them. This is for the flip-flop, edge triggered, so you can see the clock pulse is applied here, and the circuit we mentioned, transition detector, we created here to get the edge. So now the edge is applied to the input of the flip-flop. Again, the same thing here. You need to add another column. And you say Qn plus 1 measured. So here also, 1, 1 not allowed. Not allowed. And then you will say Q. I think in this case, both of them are on. Which are not allowed, of course. Okay. So this is what we need. Now let us look at the simulation. Any question here? is, and you put the conclusion, of course. Any lab, you must put the conclusion. Conclusion. Any lab, you must add the conclusion, even if it is not listed clearly here. We mentioned any measurements, any labs, we have to put our comments. Conclusion. What you see? If there's something like here, you can focus on the case 1-1. So this lab shows that for S and R simultaneously at logic high, the output is not allowed. I mean, this is not allowed because we don't know the output. For example, for SR latch, we see the Q and the Q inverted are off or logic low, which never happened. For SR flip-flop, we can see Q and the Q inverted, both of them are on, or logic high, which never happened. So this means S is 1 and R is 1 at the same time is not allowed. This is a remarkable thing we should focus on. For example, if you don't see anything, you just again summarize what you did. Okay. But again, this is like needs to highlight on this case for 1-1. Everyone sees the simulation here?
I see
Okay,
it.
good. So we can create the circuit or using these gates. So again, if you click here, so we need these gates, we need switches, we need the lights, we need VCC, we need ground. So if we go to basic here, and we need, what we need here? You need to go to the sources. You don't need anything here. So power sources, ground, so you can drag the ground here. And then you need VCC, you see VCC here. Okay, drag VCC here. So we're done with this. Then we need if you go to TTL, if you click on TTL, we mentioned this technology, transistor to transistor logic. So you see here, number, and besides the number, IC. This gives you IC. If you click here, you see it gives you IC. But if it is not, like without IC, this gives you gates here. So we need NOR gate with the number 7402, which is this one here. Okay, drag here, okay, drag. And we need another one. Okay. So we got 2. Then we need the light. So the light, if you click on the diode, or a LED, you can get these LEDs here. You can use this, or you need lamps here, so you can go to basic. If you click here, you can see indicators and go to prop, blue or whatever, or red. Okay, so you can get another one here. Okay. So you have all the switch. We need the switch. So again, go back to here. Basic switch here. This switch here is called SCBDT. SCBDT here. We need this one with two balls here. And as you can see, we need to rotate this to connect these to the input of the gate. So just right click and rotate. Right click and rotate. So now you got this. Okay. And then you connect these components like you see here. We did that before. So I believe you can do that easily. Okay. Okay, so now we see how we drag these components. So for the flip-flop, if turn on the circuit, if S is 1 and R is 0, so set the output to 1, output is Q. If S is 0, if R is 1 and S is 0, reset the output to 0, as you see here. 0, 0, no change. 1, 1 is not allowed. So you see 1, 1. What happens for 1, 1? Both of them are off or logic low, which never happened. Because in regular function, as long as Q is 0, Q inverted must be 1. Or Q logic low Q inverted must be logic high, or vice versa. But we can see here this strange output, which means we don't know the output. Okay. So please take screenshot for like whatever different cases and post it with your lab. Okay. Any question here?
Professor, how many cases do we need?
How many cases?
Yeah.
Just the 2 different cases for each, for the latch and the flip-flop.
Okay, just like always.
Yeah, just different cases for each one. Okay, now let us close this. For the flip-flop, for the simulation of the flip-flop, just 1 second. Okay. So this is SR flip-flop. We use the LEDs here. And for the LED, you need to connect the other terminal of the LED to the ground. But we don't need this for the probe. You can see here the circuit. We create the circuit to get the edge. So the clock pulse is inserted here. Like if you forget the function, go back to the slides and you can see the inputs and the outputs. So at the output, we got the edge, and this applied for the latch, for the flip-flop. So again, S1 represents set for set, S3 for reset, and S2 for like the clock pulse connected or disconnected. Okay. So for, of course, this clock pulse must be connected for the flip-flop to go under operation. But if it is not connected, so whatever you change the inputs, there is no change at all. So let us connect the clock pulse. So the edge is applied and turn on the circuit. This is the light, okay? So S is 1, R is 0, set means S, reset means R. So set the output to 1. So Q here is 1. If S1, if S set or S is 0 and R is 1, so reset the output to 0. So Q is 0, Q inverted is 1, of course. 0, 0, no change. But let us see 1, 1. What happens for 1, 1? 1, 1, 1. You see, this time both of them are on, which never happens. So in your comments also, you can focus on this case. Okay. And my screenshot for 1, 1 is important to show that when you in your comments, when you say is not allowed, because as we see in the screenshot, both outputs are zeros. I mean Q and the Q inverted, both of them are 0 at the same time, which is not, which means we don't know the output. Okay. Any question, please? Any question? Okay, so we still have some time, so you can go ahead, please, and try to build the circuit. If you have any question, please let me know.
Professor,
Yes, sir.
in the lab packet, under the second portion, the positive edge triggered SR flip-flop, it has indicators. It doesn't have LEDs that are connected
No,
to
we have
ground.
LED.
But
We have,
we need to do it the way you have it on your screen.
it's not necessary. You can use probe also here.
You can use
But we
probes.
have LEDs. You can get LEDs also.
Okay.
But it's not necessary to put LEDs. You can use the same as the one we used before, sub-probe, either red or whatever. What is that? Yeah, both of them are there. Yeah, both of them are there. I just changed to see we have different options here. But you can use both of them probes or both of them are LEDs, is okay. Such that you have indication for the output. Okay. Any other questions, please? Okay, I am with you up to the end of the class, so go ahead. If you have any question, please let me know. Let us go back to the latch first, and then, yeah, let me see. Okay.
Professor?
Yes, sir.
For the second positive edge triggered SR flip flop, when we like play it in multisim, it's like very fast, right?
It's very what?
It's very fast. Like the LEDs are flickering very quickly.
Okay, let us go back to the second one. Let me close this.
I mean,
Just 1 second, please. Okay. So the output, it depends on the two inputs, S and R. So what do you mean very fast? What do you mean by very fast?
that looks different than the one in the. Did I do this wrong? His is wired. Oh, is that
So
not
when
grounded?
you connect this, so S is 1, R is 0, so output is 1. And stay until you change the input. Okay.
Mhm.
Because this, please let me finish, and then you can talk, you can discuss with me. Okay. So it's not counter. You may talking about the counter. We will do a lab for the counter. Okay. And yeah, you can see the switches or the lights like fast from on to off, but we can control this. We can control this by controlling the frequency of the clock pulse. We'll see this. I will show you when it is fast and how we make it slow down. Okay.
I see it. Yeah,
But
no, it's just
this
because my
this
inputs
in
were
the
wrong.
counters. This happens in the counters. Okay. But here it depends on your connection.
No, I just had I had everything ground at the beginning, everything low,
Okay.
and
Okay. Yeah.
it just
As you
flickered.
see here, if you change here, so and stay until you change the input. Okay. But you
Okay.
should start with the latch first. Start with the latch first. Okay. Anyone has other comments? Any clues? Okay. So as I mentioned, either use lead or the probe. It's the same thing. Okay.